Good afternoon, everyone. Welcome to exciting, overcast, rainy Monday afternoon of Chem 170 with your host, me, Dr. White. All right, as I sent out an announcement last week, I'm postponing test number one. It won't be this Wednesday, it will be the following Wednesday. I'm looking at a calendar, the 21st. And the way I'll be giving tests is at the end of the lecture on Wednesday in lab, I will send out an email with a password that you can obviously that you can use from the downloaded test number one PDF file that will be in the assignment area of One School D2L that will be available next Tuesday sometime. Once you get the password, you'll open up the test, you'll take it, you'll have until 11 a.m. the next morning to upload as a single PDF file the test. Now, if you don't have a printer, guess what? Just on a piece of paper, write down the problem number and your answer. And if you don't have a scanner, I have ways and I'll have files, just like you've done for the labs. I will put those where you can take a picture of your test answers and then upload it as a PDF file. But don't forget, test number one has been postponed by 1 week. And that happens often. The first test, I'm usually off by a week. I don't know why I don't just say, this is what I think I'll do, and then make it a week later, because that's going to happen anyways. All right. Don't forget, hand in labs. I've graded it, and sometime tomorrow, I'll post the lab scores for lab number one. And don't forget, the lab we did last week is due this Wednesday. Keep up. Labs are easy points. All right, game plan for today. I'm going to be going through the alkenes, alkynes, double bond, triple bond problem set. After that, we'll get back to aromatic compounds, which I'll finish today. And most likely, if I do finish today, which I think I should be able to, this Wednesday, I will go through the aromatic problem set. Also, a week from today, the Monday before the test, I will do my world famous review for the next test. Now, one of the things I forgot to do, bad Dr. White, was I forgot to send out an email. So I'm going to postpone until this Wednesday. And I wrote, hold on while I'm doing that, talking to you. I'm going to write a post-it. This goes on my bathroom mirror, so I know to do it. And what I will do this Wednesday, beginning of the lecture, I will teach my method how to eliminate test anxiety. It works real good. Students have been using it for a number of years. If I had a lot more money, I'd try and sell it, but I don't. So it's all in the marketing and advertising, which I just don't have those kind of funds. But anyways, I will teach that method. And if you get nervous during a test, I've had students go from F's and D's or barely C's to A's and B's. And it's good for not only Chem 170, but other classes too. Now, I will cut it out of the video. I like my special effects. Cut it out of the video, but you can come to my office hour this Wednesday or next week, and I'll be more than happy to teach it to you. All right, what I'd like to do now is go through the alkenes problem set and the alkynes problem set. They're all together. And let's go through it. Now, on test number 1, and between now and Wednesday, I will post a breakdown of how many problems, how many pages, and what type of points there are. There are 3 areas that I give points on or ask questions about. And I should mention this. Every question on my test, I've covered the concept at least twice, usually a lot more in lecture. Now, there are 3 types of questions I ask. The first one is general knowledge, like how many bonds to carbon? Hopefully all got that down. The next type is nomenclature. Nomenclature, you know by now, means naming. There are 2 types of nomenclature question. One is, here's the molecule, give the IUPAC name. The other is, here's the name, draw the molecule. And finally, the third type is here, give the organic product or products for the following reactions, where you have to predict what is being made. Now, on test 1, I'll have one different type of question for reactions, and that is give the starting material or materials for this reaction. Now, if you look at my practice problems, I never include problems like that. Why? Look at the practice problem with answers, cover the starting material, look at the answer. You now have your synthesis problem to work on. Again, they're a lot harder. So test number 1, I'll only give 1 practice problem. All right, thumbs up, person. Thank you, you see it. All right, let's do the following, and this will be a nomenclature question. Give the IUPAC name for the following. What you should be doing now is look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. And if we look at A, 1A, double bond, you count the longest chain with both carbons double bond. In this case, there's only one chain. 4, we call that butane. Drop the ANE ending, that replaced with ENE, butene. Then the carbon, a double bond closest to the end, is the number you put in front here. Here it's 1. Now, I'll talk about cis and trans later, but when you have 2 of the same atom or group on one carbon and double bond, you can't have cis or trans, which is why there's no cis or trans here. Next, we have a ring. What do we have? How many carbons in the ring? 6. Hexane. It's a ring, cyclohexane. It's a double bond ring. Drop the ANE, replace it with ENE, cyclohexene. Now, there's no number in front because when there are no other functional groups, which will happen in this class, one of the carbons double bond has to be 1, the other has to be 2. And you do it in such a way that you give the substituents the lowest numbers. So if I make this carbon 1, this 2, it'd be a methyl group on carbon 1, ethyl group on carbon 2. So the correct IUPAC would be 3-ethyl, 1-methyl cyclohexene. Now, if you had put down 1-methyl, 3-ethyl cyclohexene, I'd give you full credit. Next, a double bond again. How many carbons long is chain? 1, 2, 3, 4, 5. Remember, just because it bends, this carbon is still connected to that carbon. They're linked together. So there's 5 carbons, pentane. It's a double bond. Drop the ANE ending, put ENE, pentene. Which carbon in a double bond is closest to the end? This one. If this is carbon 1, this is 2. And therefore it's 2-pentene. Now notice there's a hydrogen on each carbon of the double bond. When you have one the same group or same atom on each carbon of the double bond, if they're below a plane, like this line, if there was one right there, or on the same side, they're cis. When they're opposite, they're trans. These are on the same side, they're cis. Therefore, this is cis-2-pentene. Now, if you look at D, I played a trick, not really a trick, wanted to illustrate something. Notice we have a double bond. The longest chain is 1, 2, 3, 4, 5. Pentane becomes pentene. The carbon closest to the end of the chain would be carbon 2. And on carbon 2, we also have a methyl group. But notice this first carbon of the double bond. It has 2 CH3 groups on it. As soon as you have 2 of the same group or atom, you cannot have cis or trans, because the hydrogen is cis to the methyl group here, but it's also trans to this methyl group there. So this does not need cis or trans. Don't forget, if you want me to do a problem I haven't done, please feel free to ask. Now, the second type of nomenclature question is draw the condensed structure, meaning don't put on carbons, hydrogens, single bonds, don't show those, for the following IUPAC names. And here we have cyclohexane. How do you decode this? Start at the right, move left. ENE ending, double bond. If that were ANE, cyclohexane is a 6-membered ring. And cyclohexene, 6-membered ring with a double bond. Now, since the ring can rotate, now I wrote this answer. This would be correct. This would be correct. I'll just do one more. I could do another one. All you're doing is rotating the ring around. So any one of these would be correct. I just felt like drawing that one, but most of you probably did that one. All right, let's look at C, 5,6-dimethyl trans 3-octene. How do you decode this? You start from the right and move left. ENE ending, double bond. That were ANE 8 carbons. Where does the double bond start? Carbon 3, and it's trans. So 1, 2, 3, double bond, and 5, 6, 7, 8. Now notice I have the 2 hydrogens on opposite sides, and these 2 carbons and these 4 across plus 2 methyls are on opposite sides of this plane, going right here. And that's because of trans. Now, if we number this 1, 2, this carbon's 3, this is 4, 5, 6. Now, as I go right to left, I see methyl. Ooh, I know that's CH3. Dimethyl, di means 2, tri means 3. So there are 2 methyl groups, and where are they? On carbons 5 and 6. And that's how you do it. Now, I made a mistake. Shh, don't tell anybody. On D, that really should be 2-tert-butyl 3-isopropyl cyclopentene. And that's my mistake. The 2-tert-butyl should have gone first. But the structure still gives you the same. We have ENE ending, cyclopentene, double bond in a ring, 5-member ring. Remember, each bend in a line is a carbon, each end in a line is a carbon. And what do we have here? Next, you should have seen 3-isopropyl. So if this is a double bond, that'd be carbon 1, that'd be carbon 2, and then the isopropyl, and I'm also missing a hydrogen. Oh, don't look, don't look, don't look, don't look. But anyways, that should be CH right there. And on carbon 3 is the isopropyl, on carbon 2 is my tert-butyl. Now, if you notice over here, and you'll see it more often for rings now, I had some students that said, well, how can I draw that all in the line method? And so I started putting it on the problem set because a couple of them got upset when I didn't talk about that. And the last thing I need in the world is an upset student. So I put those in there. All right, next, let's talk about reactions of double bonds. If I have a double bond and reacted with height, well, let's look at this molecule, look for what's different. Boy, I just saw it like that because I've been doing this a few more months than you have. A few more months. And what's different? A double bond. Reacting with hydrogen, nickel, anhydrous nickel. That's the catalyst. I should have put down here, the catalyst can be nickel, platinum, or palladium, PT or PD, but I didn't. And what happens? Remember, there's a pi bond. You break the pi bond. Each carbon of the double bond gets a hydrogen. And do you break carbon-carbon single bonds? No. So if I start with 4, I better end up with 4, and I do. Now, I wrote it this way, but an easier way you could have done here are your 2 carbons, double bond. Each one gets a hydrogen. Excuse me. And there are 4 bonds to carbon, so I know how to, and this way, it's less work for you. Either way, you can do it with the hydrogens hanging down like that, or you can bring them up to CH2, CH2. Okay? And if you notice in B, I have the same reaction, a double bond, look for what's different, hydrogen and catalyst. Now in a ring, since you don't show hydrogens, when I break the pi bond, here's how you draw it. I think I'm going to tell you a deep, dark secret. If you want to know how to make your own practice problems, you want extra ones, you can do your own. Just think about, like if you have a double bond, you want hydrogenation, and I want to practice this reaction. And if I want to practice this, I say, all right, let me draw a molecule with a double bond. And I think, do I want it in a ring or not? I'll say, I'm not. And how many carbons? Pick a number between 2 and 10. 7. And where do I want to put the double bond? I'll put it here. You put it anywhere. Do I want anything on there? Yeah, let's put a methyl group here. And now I'm going to react it with hydrogen and pick a catalyst. Remember, you're choosing to practice, oh, let's try palladium. We could have picked nickel or platinum. And I'll let you try and figure this one out first. See, I'm going to share the fun today. What would be the organic product or products of the following reaction? Wonder where all your colleagues are, Ignacio. Well, it is a net class. So, and when you're all done, give me a thumbs up. All right. So remember, you're doing your own practice problems. Hey, look, what's different? Double bond. Here's the general reaction. Do you break carbon-carbon single bonds? No. Add 3, 7 across. I still have that methyl group on this carbon, but my general reaction tells me between these two carbons, double bond is gone, and each one gets a hydrogen. And now I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And there you go. And that's how you do it. So if you ever need more practice problems, you can do your own. Well, how do you know you did them right? Well, come to my office hour or see me after class. Now, the next one is C and D. Let's do D. Now, D is chemistry instructor's favorite trick on a test. Put a big, scary molecule on there. If you don't know what's going on, that's a big, scary molecule. But you look for what's different. What's not a carbon-carbon single bond or a carbon-hydrogen atom should get your attention like that. And what do we have? A double bond. We're reacting with bromine, the general reaction, and here I should have put X can be fluorine, chlorine, or bromine. Double bond, halogen gas. You break the pi bond, and each carbon of the double bond gets a halogen. And therefore, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across, 2, 4, 6 across. Now, here are my 2 carbons of the double bond. I broke the double bond. By the way, the methyl groups are still on those 2 carbons. I broke the double bond, and each atom gets a halogen. Well, in this case, the halogen is bromine. And I put in the hydrogens. And that's how you do it. And the one above it is even simpler. Now, let's look at E. E, we're reacting a double bond. If we look at the starting material, it's got a double bond. Everything else, carbon, hydrogen, and carbon single bonds. And we're reacting with HBr. Hydrogen bromide is HX, an acid, where X can be chlorine, bromine, or iodine. and you break the pi bond, and one carbon gets H, the other gets X. How do you know? It follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen. Now we got to do some high-level math. How many hydrogens on this first carbon double bond? 2. How many on the second carbon? Well, just that one, 1. Which is the greater number, 2 or 1? Hopefully I'll pick 2. So the hydrogen will go to this carbon, the halogen will go to this, and you'll lose double bond. So I have 3 carbons, 3 carbons. Hydrogen goes to the end, lose double bond, and my halogen, in this case Br, goes to the center carbon. And that was Markovnikov's rule. Now, if we look at F, remember Dr. White and Mother Nature love rings, students don't. Why? Because I don't see any hydrogens on that ring. You've got to count them and figure it out. And let's go to my whiteboard here. Which halogen was I using? I forgot. HI. Wrong board. Right board. So I look at this molecule, what's different? A double bond. Reacting with HI, iodine is a halogen. For this reaction, X is chlorine, bromine, or iodine. And you break the pi bond. One carbon gets H, the other gets X, and it follows M's Markovnikov's rule. The carbon of double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen. Well, here are my 2 carbons double bond. I don't see any hydrogens. Well, there's 4 bonds to carbon. This top carbon has 1, 2, 3. 4 minus 3 is 1. So there'd be 1 hydrogen on there if I was showing hydrogen. I'm not. And if we look at the second carbon, there's 1, 2, 3, 4. 4 minus 4 is 0. No hydrogens. Now, which one is the greater number? Hopefully I'll pick 1. Well, do you break carbon-carbon single bonds? No. So still going to have the ring, still going to have the methyl. So I told you more people would show up eventually. Hi, Andrew. But anyways, we've lost the double bond, and 1 carbon will get the H, the other gets the halogen. And in this case, this was the one with 0 hydrogens. So the one with the less hydrogens gets the halogen. And the other carbon right here gets the hydrogen, but we don't show that on a ring. And if you look at this carbon, how many bonds to that? 2. How many bonds should there be to carbon? 4. That means there's 2 hydrogens on there. We went from 1 to 2, so we did put it there. And that's how you do it. Now, the next reaction I'd like to go through is H and I. Let's do I first. And what do I have? Or wait, I have a simpler one. Let's do G. What do I have that's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? A double bond. Reacting with acid, H plus means acid, and water, H2O. Now, double bond, acid and water, think of water as HOH. And you break the pi bond. Remember, double bond has one pi bond, one sigma, and each atom or carbon of the double bond gets something. The carbon with the most hydrogens gets the hydrogen, Markov-Nichols rule, and the other gets the hydroxyl group. So if we look at G, the carbon all the way on the right has two hydrogens. The one next to it has one. Which is the greater number? Hopefully you all know it's 2. So the hydrogen will go on here. Remember, water is HOH, and that OH will go to there. And that's what happened. And that's how you do it. Now, in a ring, again, you have to count carbon hydrogens. And here, this carbon has how many hydrogens? Count the lines. 3. There should be 4 bonds to carbon. So there's 1 hydrogen up here. Here, count the lines. 1, 2, 3, 4. 4 minus 4 is 0. So the hydrogen goes up here. The hydroxyl group goes here. Now, if you switch the hydroxyl and methyl, CH3 right here, that would be okay. Water break. All right, now let's talk about triple bonds. One of the things I should have pointed out earlier, and I will now, but first, time to be subtle. Don't you like when I'm subtle? Hint, know this. And I didn't write it there, but all the general reactions we just went through, you should know. And you should know a double bond has 1 pi bond, 1 sigma bond. A triple bond has 2 pi bonds and 1 sigma bond. And you should know this. Now, let's look at IUPAC nomenclature. If we look at A, the IUPAC name, not the common name, I'm asking only for the IUPAC, 2 carbons, ethane, triple bond, ANE ending becomes YNE, ethine. Now, this is the only example, or 2 of them, where you don't need a number. Why? Because you can't have 2 ethyne. There's only 2 carbons, and one of them is always going to be 1. Now, if we look at B, we have 1, 2, 3, 4, 5 carbons. Notice the triple bond, 5 is pentane. Triple bond, ANE ending becomes YNE, pentyne. And what carbon in a double bond is closest to the end of the chain? And therefore, that's 1. Now, if we look at C, again, triple bond. How many carbons longest chain? 1, 2, 3, 4, 5, 6. Wait, I counted wrong. 1, 2, 3, 4, 5, 6, 7. And 7, alkane is heptane. You drop the ane ending, put yne, heptyne. Which carbon of the triple bond is closest to the ends of the chain? And it's this one with the 3 above it. If this is carbon 1, 2, 3, I want the other way, be 1, 2, 3, 4. And you go the numbering in such way, you get the lowest number. And that would make that 3 heptyne because the double bond started at carbon number 3. Now we have, oh, look, it's your old friend, the methyl group, CH3, and it's on, if this is carbon 2, that's carbon 3. And similar here, except you have 2 methyl groups on this, you have 2 methyl, that's used the prefix di, 3 would be tri, and they're both on the same carbon. But whenever you see di, it means 2 numbers, even if they're on the same carbon. So it'd be 2,2-dimethyl 3-hexyne. Here we have 6 carbons in the longest chain. Now, there's 2 nomenclature questions. One is, here's the structure, give the name. The other is, here's the name, which can be common, and draw the structure, or IUPAC. Now, acetylene is the common name. This is for, I believe, test number 1. It's the only common name I'm asking you to learn. And that's the simplest of all alkynes, 2 carbons with a triple bond. Now, there's one other way you could draw that. On the answer key, I have this. Now, on the left carbon, all the way to the left, this one right here, you can move the hydrogen right justified. And this is the other way. Either way would be correct. If we look at C, how do we determine, by the way, there's no sister trans in triple bonds. I haven't seen in decades a paper where there's a triple bond in a ring, so I'm not going to give you any. All right, how do we decode 2,2-dimethyl? And there should have been a dash after the 5. Don't tell anybody. But anyways, 2,2-dimethyl 3-heptyne. How do we decode this to know what to draw? You start at the right and move left. YNA ending, triple bond. If we're ANE, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. And then the triple bond starts at carbon 3. And most of you are going to start from the left, 1, 2, 3. So that's what I did. And there's my triple bond. And then there's methyl, CH3, di means 2, and they're on carbons 2 and 5. And if this is carbon 3, this is 1, 2, 3, 4, 5. And that's how you do it. And this one's similar, D. All right, now let's look at the reactions. Remember, they're not 1, but 2 pi bonds. And since organic chemists do not want to balance equations, we get lazy and put down, well, do you need a lot of hydrogen? Bracket, letters X, S, close bracket means excess. That means you have all the hydrogen in the world that can react with anything hydrogen can react with. In this case, a triple bond. You break carbon-carbon single bond? No. So I have 3 carbons, break the 2 pi bonds. Each carbon gets a triple bond. Now, I forgot CH3 over here. Now, oops. And the same thing for B, triple bond, 2 pi bonds. I break the pi bonds. Each carbon gets a hydrogen. Everything else stays the same and comes along for the ride. And I forgot to put the catalyst on there. Sorry. All right, let's do C. What do we have that's different? A triple bond. Remember, when you look at molecules now, you should be looking for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention. Ooh, like that. That was better. And we have a triple bond reacting with Br2, that and the letter XS. Br2 is a halogen, X2, where X can be fluorine, chlorine. I lost my train of fluorine or iodine. And we have excess again because we have 2 pi bonds. And we break each pi bond, each carbon and triple bond gets 1 halogen, 2 pi bonds, each carbon of the triple bond gets 2. And if you notice, do you break carbon-carbon single bonds? No. Each carbon of the triple bond receive 2 halogens. I'm trying to scroll it down. I'm on the last page. That's why I won't scroll down. All right. And if we look at D, I did the chemistry instructor's favorite trick on a test. What a big, scary molecule. But if you look at that big, scary molecule, it's not scary. It's got a triple bond. And as soon as I see that, nothing else, carbon single bonds, or hydrogen and carbons, I know I'm dealing with this reaction. Right to 2, not 1, 2 pi bonds. Each carbon on the triple bond gets a halogen. I have 1, 2, 3, 4, 5, 6 across, 2 methyl. I break the 2 pi bonds, and each carbon of the triple bond gets not 1, but 2 halogens. And that's how you do it. Any questions? Well, in that case, let's get back to aromatic compounds. Let me close this first. All right, everybody say symbols or structures for benzene. Thank you, Nasha. All right, remember, aromatic compounds for this class have a 6-membered ring with conjugated 3 double bonds. Conjugated means alternating single, double, single, double, single, double. And the one on the right for benzene is the kekulé structure. The one on the left is the circle, shows the double bonds holding hands, or electrons really, in the 3 double bonds. And either way, this would be a way you write benzene. Now, let's talk about the nomenclature of aromatic compounds. It gets a little different. The names of some of these aromatic compounds have been around for eons, long before IUPAC came around. So IUPAC, in their infinite wisdom, says, well, everybody's calling this molecule benzene. We'll make that the IUPAC name. And they did. Now, if I were to write and watch closely, draw the structure for benzene. Well, benzene is a six-membered ring with alternating three double bonds. You can draw it this way, you can draw it this way. These are resonance formed, they're really the same, but all you're doing is shifting electrons, or you can show it with the pi cloud like that. Now,
I don't think you're showing whatever you're doing.
oh no, I forgot to ask the thumbs up people. Now you see that? Let me do that again. Thank you very much, Ignacio. That happens once in a while. I got to remember always when I change screens, ask my thumbs up people. All right, let's do this again. If you were to be asked, draw the structure for benzene, you can write it like this. It's resonance form, or you can draw it with the circle. The first two I like better than the third one. That's just my personal choice. Now, what I was getting at is common mistake. On test number one, people draw this, and this is wrong. See, it even says it on the screen wrong. Why? Because this is cyclo. Oops, got real small there. Sorry about that. This is cyclohexane. You have to have the double bonds or the circle inside. If you don't, this is cyclohexane, not benzene. That's a common mistake on test number one. I'm telling you this so you don't make it. Again, benzene has double bonds, cyclohexane doesn't. Oh no, I went a whole minute over instead of break time. I'll have to just extend break time. Let's take a 5-minute break, come back at 1:56, and I'll see you in 5 minutes. And we'll continue on with aromatic compounds. Bye now for 5 minutes only. time to get going. All right, welcome back. We're talking about aromatic compounds. Remember, they're called aromatic because the way they smell. Why? Because they originally came from herbs and spices. Now, this is the structure, and I better ask, everybody see benzene on your screen? Thank you. This has been called benzene for eons, and IUPAC said, all right, we'll call it benzene. And they did. Now, if you put a methyl group on there, do you call it methylbenzene? And the answer is no. Why not? Because for many eons, the molecule with a methyl group on a benzene ring was called toluene. Therefore, whenever you see a methyl group with a benzene ring, its IUPAC name, which was also the common name, is toluene. Those you should know. Now, I'm going to show you a couple others. I'm going to turn the switch. Will that be on test to the off position? Now, when you have a double bond on a benzene ring, the common IUPAC name is called styrene. Again, switch is off. How many of you ever heard of polystyrene? Have you ever seen those white insulated cups or the really inexpensive white lightweight coolers? They're made from polystyrene. How did I get that name? Poly means many, and there are a lot of these molecules hooked together to make that. A lot of things in your daily life are named from organic molecules they're made from. Now, you can use numbers when there are two or more groups, but most people, organic chemists, use special names instead of numbers for two groups on a benzene ring. And let me show you something. And bear with me, this is going to take a little while. And remember, everything you see here will be on the video, so you can always pick it up later. And if we're in a classroom, you'd be watching me write this on the whiteboard. Ooh, one thing I neglected to talk about, and I'll come back to, let's do these first. So if I look at, let's call them A, B, and C. I have a benzene ring. I have an ethyl group and propyl. And on B, we have an ethyl group and propyl. And it's a benzene ring. And C, guess what? We also have an ethyl group and propyl and benzene. But they're different. As I mentioned earlier, when we were talking about cis and trans, IUPAC has set up a system that no two different molecules have the same name. Well, let's look at what's different here. If I call that carbon 1 the other substituents on 2. I call this 1. The other substituent is on 3. If I call this 1, the other one is on 4. Running out of room here. Now, this came long before IUPAC and still being used. And disub meaning disubstitution. When something is 1,2 disubstituted, it's called ortho. Therefore, A is called ortho ethyl and propyl benzene. Except for Aldridge, nobody uses numbers. So I'm going to ask you to learn these 3 prefixes. Now, for 1,3 disubstituted, we use the prefix meta. So B would be meta ethyl benzene. Ooh, an E fell off the end here. I'll put it back on. And finally, if we, again, 1, 3 disubstituted, 1, 2 disubstituted. And the last one is 1, 4 disubstituted, and that's called para. So that's 1, 4 disubstituted. 1, 2 is ortho, 1, 3 is meta, 1, 4 is para. And hint, you should know this. Now, in all of organic chemistry, ortho, meta, and para are only used for aromatic compounds, not on cyclohexane rings. How that evolved, I have no idea. Just like, why do we call this a bottle? Why don't we call what's in my hand a door? Somebody came up with names for things. And that's how this ortho, meta, and para, but it's stuck. Now, before we practice this, let's go through some basics. All right, first one, what do you see? A 6-membered ring with 3 double bonds that are conjugated. Conjugated means alternating single, double, single, double, single, double. And no, this is not cyclohexatriene, it's benzene. Now, when we have an alkyl group on there, you name the alkyl group and the name benzene. Doesn't matter which carbon when there's only one group on there. And if you notice, what do we have up here? An N-butyl group. And what do we have here? 6-membered ring, 3 double bonds that are alternating, single, double, single, double, single, double. So that's benzene, and 4 carbons to the N carbon is then butyl. And this should be B, not C. This should be C. And here's one for you to try. What would be the IUPAC name for C? And when you're done, give me a thumbs up. If you're done early, we'll give everybody time to finish. Ah, everybody's finished. All right, what do we have here? A benzene ring. And 2 carbons is ethyl. And that's ethylbenzene. Oh, let's do another one before we get to the tough stuff. One more for you to try. What's the IUPAC name for that molecule? 3 points each. And when you're done, give me a thumbs up. I guess you can also give me a thumbs down. Wonder if they really did that in Roman times, in the Colosseum. Probably must be. Thank you, Andrew. All right. If you put methylbenzene, you're wrong. Methyl group on a benzene ring is called toluene. And that's the IUPAC name. They catch anybody? Well, that's why I gave the example. Now, before we go further, there's something I need to talk about benzene and toluene. Both are liquids at room temperature, and they've been used for many eons as solvents and other things. There's a problem. They're very hazardous chemicals. When you inhale the vapors, they attack your organs like your liver and kidneys, and they rot out, and I'm not a medical doctor, they attack your brain and do serious damage there. Now, for many years, until the 1950s, late 50s, when latex paint became popular, paint had benzene or toluene as the solvent, the liquid, the pigments that make this wall the color it is, white in this case, that color. Well, unfortunate, sad story. When I was about 8 or 10, there was one of my cousins of my mother on that side of family who all his life had been a painter. And from inhaling all the fumes from benzene and toluene in the paint, it had destroyed his brain. And he was only in his early 60s, late 50s when I met him. And he was about one step up above a vegetable. He barely could communicate. It was very sad. And luckily, people now know the dangers of the vapors of benzene and toluene. Now, how many of you, and I never met anybody in my life who've been, but how many of you have ever heard about people who sniff glue to get high? They're called glue sniffers. And what they're sniffing is toluene. And if you seen in the past news reports about people sniffing glue, it would rot out their brain, like my uncle, or not uncle, cousin. It wasn't my mother's brothers. But anyways, a lot of things I think they've taken it out, but still, I don't know if airplane glue still has that. Let's take a look real quick. Yeah, here they have the old one. I think the new one, they've gone to methyl ethyl ketone. I'll teach you about that later. But the old ones, here they have some packages of old ones. Like when I was a kid, they were selling this. They had toluene, and they say we're minor. No, if you were sniffing enough of it, it wasn't minor. But anyways, I just wanted to share that with you. Certain chemicals can be dangerous, and unfortunately, it takes time for those. Now it's faster, but in the old days, before enough people got sick, uh, for that to happen. Uh, I think most of you are too young to remember 9/11. Most of you either weren't born or just a couple of years old. I wasn't. In fact, I just started consulting plus teaching, and I was home that morning. 9/11 was yesterday, one of the two saddest times in my lifetime for our whole country. Obviously, when my parents passed away, that was a sad time for me personally, but in our country, 9/11 and the other one that I lived through was when President Kennedy was assassinated. That Friday, I can still picture it, was also a very sad day. But when 9/11 happened, I was working and a friend of mine called me and said, "You're home, right?" I said, "Yeah." He said, "Go down, turn on your TV. You got to watch this." And I did. And the first tower had just been, the plane had run into that. They weren't sure was it an accident or anything like that. And I was glued to my TV set watching this. And live, I saw it live, and it was quite sad. The second plane hit the second tower. And at that point, everybody knew it wasn't an accident. It was a terrorist thing. But well, just thought I'd share that with you. Now, let's go back to disubstituted. When you have 1,2 disubstituted, it's ortho. 1,3 is meta, and 1,4 is para. So let's do the following, which I need to show you. Now, if you look at this molecule, you have a benzene ring, 6-membered ring, 3 double bonds. I don't use a circle, you can, but I don't think it looks cool. I'm showing the double bonds because it looks cool. Now you know he's an organic chemist. How many people would think it's cool or uncool? Dr. White does. All right. Now, when it has a methyl group on there, it's no longer benzene, it's toluene. But it also has an ethyl group. Now, interesting enough, for ortho, meta, and para, when there are two groups, even though the methyl group is included in the name toluene, this is still considered a disubstituted benzene ring, even though it's not named. So notice this is 1, this is 3. So 1,3 would be meta. So this is called meta ethyl toluene. Again, even though the methyl group is included in the name toluene, it's still considered a disubstituted benzene ring, and you use ortho, meta, and para. If we were in the classroom, I'd be writing this in one corner of the board. How many of you ever heard of Ortho Pharmaceutical Company or drug company? I wonder where they got their name. Hold on, let's go to the internet. And it's part of Johnson & Johnson now. Ortho Pharmaceutical Corporation. And I wonder where they got their name. Hopefully you figured that out by now. And you'll find a lot of names of chemical companies come from nomenclature. Remember, ortho is 1,2 disubstituted, meta is 1,3, para is 1,4. And let's try this one. What would be the IUPAC name for the following? And don't forget, the lab is due this Wednesday that we did last week. Sometime today or probably tomorrow, I'll post in D2L your scores because I graded the labs already. Since I can't hand them back, what I do is, if you have any questions about anything I ever grade, just come to my office hour and I'll be more than happy to discuss that. And if we were face to face, I'd say the same thing. Come to me and ask, why did I get this score? I'll be more than happy to answer that because in my universe, there's no such thing as a dumb question. And when you're done, give me a thumbs up. All right, let's get to work. What do I see here? A benzene ring. And I see here an ethyl group and 3 carbons. The center carbon is isopropyl. Now, if you had written down isopropyl ethyl benzene, I'd give you full credit. But we're not, excuse me, something went wrong, down the wrong way. I guess I'm choked up over this molecule. But that was awful, sorry. But anyways, we're not done. Notice, whichever way you count, this is 1,4 disubstituted. What's 1,4? Para. So that would be para ethyl isopropyl benzene. Again, benzene ring, isopropyl ethyl, and 1,4 disubstituted. See, it even says it on the board. but that was hokey. It's para. All right, let's try another one. And let me just write. And this is the disubstitution. And here's one for you to try. What would be the IUPAC name of that molecule? And don't forget, tonight I have my office hour. And if you think of a better time, you'd like me to do it one on Monday from 5 to 6:15, one on Tuesday, maybe a little different time in the evening, like from 6 to 7:15, let me know by email if that would work out better for you. And don't forget, when you're done, let me know. All right. So if we look at this molecule, what's different? Ooh, a 6-membered ring with 3 conjugated double bonds. That's benzene, but wait, there's a methyl group on there. And a methyl group on a benzene ring is toluene. And then over here is an ethyl group. And now, notice this is 1, 2, 3. 1,3 disubstituted is meta. So this would be meta ethyl toluene. Let's go through that again. Benzene ring. No, because you also have on that benzene ring a methyl group, and that's called toluene. Remember, toluene has this structure. So, excuse me, we have a disubstituted ring, and the second substituent is ethyl. So that would be meta-ethyl toluene. Now, the following, do not write down unless you really have to. You don't. Everybody know what that is? Of course. It's, remember, this is 1,4. It's paramedic. You can groan, it's permitted. That was pretty bad, but I have to keep them clean for the class. All right, now let's continue on. Now, there's some new substituents I'd like to teach you that I didn't have earlier, and that's when you have halogens. When you have a chlorine on something, it's called a chloro group. When you have a bromine, it's called a bromo group. Iodine is iodo. Fluorine is fluoro, which I always spell wrong. I put the O before the U. I was never good at spelling. It's one of the few organic things I always misspell. And a new group, NO2, where the nitrogen is bound to the ring, or this could also be on a straight chain, but I didn't cover it earlier. And one I won't ask you to learn, but I would like you to know, that's sulfonic, sulfur with 3 oxygens and a hydrogen. So you should know Cl is chloro, Br is bromo, iodine I is iodo, F is fluoro, and NO2 is a nitro group. And those are just like your methyl, ethyl, and others, substituents. But now, since there are no carbons, we can't call them an alkyl group. We just call them substituents. And what would be the IUPAC name for this? Well, I have a benzene ring, and Br is bromine, which is bromo. And you'd have bromobenzene. And why don't you try that? That's Cl. I just don't know how to print Cl, so it looks nicely lowercase. So I always just use script or cursive. And in case you forgot, here's what Cl is. Chloro. So what would be the name of that compound? And don't forget this when you're done. I had to train you people better. You'll get the hang of it. And when you're done, don't forget, give me a thumbs up. All right. What's Cl? Well, we got a benzene ring here, 6-membered ring with alternating double, single, double bonds. That's benzene. Cl is chloro. Since it's the only substituent on a ring, you don't need a number. Now, I'll do this one. And what do we call that? Well, I've got a benzene ring here. And then what's NO2? That's a nitro group. So that would be nitrobenzene. So the halogens, bromo for bromine, chloro for chlorine, Cl, I is iodo, F is fluoro, and then NO2 is a nitro group. And why don't you try this one? I'll let you try this one. What would be the IUPAC name for that molecule? When you're done, don't forget, give me a thumbs up. I have to make a sign that I hold up to the camera. When you're done, give me a thumbs up. And here, what do we have on here? We've got a benzene ring, but it's got a methyl group, and that's toluene. And I've got a chlorine on there, and that's called a chloro group. And it's 1,2 disubstituted, which I should have written the chart for you, sorry. And that would be orthochlorotoluene. I don't have it on here, but when you have more than 2, you use numbering. And when there's a methyl group on a benzene ring, that's usually carbon 1. And let's look at this molecule. What would be the IUPAC name for that? Well, I have a methyl group on a benzene ring. That's toluene. I have a nitro group, NO2. No, I've got 2. No, I've got 3 of them. And remember, di is 2 prefix. Tri means 3. So there's trinitro, NO2 is nitro. And now if this is 1, this is 2, this is 4, this is 6. When you see tri, you need 3 numbers, di, 2 numbers. So this would be 2, 4, 6, trinitrotoluene. 2, 4, 6, trinitrotoluene. Hold on, I need some water. This is really hard to say. 2, 4, 6, trinitrotoluene. Did I tell you how lazy organic chemists are? Why don't we call it this? TNT, which is a common name, not an IUPAC name. TNT. That's the stuff in dynamite that makes it go boom. Explosion. Now, how many of you have ever heard of the Nobel Prizes? Give me a thumbs up if you've heard of them, or hand up if you've heard of the Nobel Prizes. Well, who started that? Thank you, Andrew. I guess you both have. And that is Alfred Nobel. And where did Alfred Nobel get all his money? Well, trinitrotoluene, 2,4,6 trinitrotoluene, is a liquid. Well, hold on, let me get you a full bottle. A liquid at room temperature, and it's very shock sensitive. Go like this, and it would have blown up, and I would have been dead. And when they first came out with it used as an explosive, a lot of people died in transporting this, because any bump in the road could possibly set it off. Well, Alfred Nobel and his brother, whose name I can't think of right now, came up with a way of mixing this with clay and other things to make a safe explosive. And if they wrapped it in paper and sticks, they called it dynamite. And I think you're all familiar with from TV. I've never handled it personally, or the movies. You need to put a blasting cap inside to make it blow up. Well, they made a lot of money, not just for mining. Once they could stabilize trinitrotoluene, 2,4,6 trinitrotoluene, you could now make very powerful bombs and explosive artillery shells. And they made a lot of money, mostly selling explosives for ammunition, for war. Now, sad thing, Alfred's brother, there was an accident at one of their plants and it blew up. Even nowadays, I wouldn't want to work making trinitrotoluene. It killed his brother, which was sad. Now, why he was motivated to donate all that money to set up the Nobel Prizes, I guess somebody you can look online. I don't know. But is there anything wrong that the Nobel Peace Prize originally was funded by money that came from war? No, money is money. That's just the fact of life. Now, let me give you one to try. And why don't you try this? Remember, Cl is bromo, chloro, Br is bromo. And it's an ugly looking 6-membered ring. Let me draw it again so it won't look as ugly. Good news, on a test, I have software that draws rings very pretty. It's called ChemDraw. I've been using ChemDraw for more than 20 years. And it's probably the best chemical or structural drawing software out there. I don't even know if they have any competition. I'm sure they do, but I don't know anybody who uses it. And when you're done, give me a thumbs up. Hint, the methyl group is 1. All right. So methyl group on a benzene ring, toluene. This is 1. The chlorine is on 2. The bromine is on 3. When you have more than 2 groups, you use numbers. So the correct IUPAC would all alphabetical: 3 bromo, 2 chloro, toluene. Now, if you switch and put 2 chloro, 3 bromo, I'd still give you correct. And that's how you do it. All right, now, there are 2 nomenclature questions. One is, here's the structure, give the IUPAC name. The other is, here's the name, draw the structure. And you've seen that in my practice problems. After test number 1, you'll understand why I call them practice problems. And why don't you try this one first? Draw the structure for benzene. Thank you, Ignacio. Better enunciate more clearly. And thank you, Andrew. All right, what's benzene? A 6-membered ring. No, that's cyclohexane. Don't forget the double bonds. There's two resonance forms I could draw, or you could just do a circle. All three of those would be correct, any one of those. And why don't you try this one? Draw the structure for toluene. And while you're doing that, I'll get to work. All right, and for toluene, you have a benzene ring with a methyl group. If you forgot the double bonds, that's methylbenzene, and that would be wrong. Now, you could also draw this resonance form, and one I rarely, like almost never use, but it would be correct on my test. That would be correct too. But you got to have something in that ring that's correct. I had students lose 10, 15 points because they forgot to put the double bonds or circle in there, which is why I'm telling you, don't forget. And why don't you try this one? Draw the structure for meta nitrotoluene. I think one person just gave me the signal. Was I right? And the other person too. This is a nice small class, very personable. Thank you, Andrew. All right, how do you decode this? Know what to draw. You start from the right and move left. Toluene, six-membered ring. Don't forget double bonds. Don't forget the methyl group. Nitro, NO2, meta, 1, 3. This is 1. You can go counterclockwise or clockwise. Most are you going to go clockwise, nitro group, and that's meta nitrotoluene. If I look at the clock, it's time for a 5-minute break. I'm going to take a 5-minute break. Hopefully you do too. And I'll see you at 2:50. See you in 5. Time to get going. I was just looking out my weather window, my front window of my house, and I see the sun started to peek out a little. Even though I am glad we got all this rain this weekend, because my lawn, bushes, trees, and evergreens are all happy now. So am I, because I don't have to water. All right, we were talking about nomenclature, and we finished that. Now, next 3 slides. Are you watching? Click. I'm turning the switch. Will this be on a test to the off position? But it will give you information to understand what I will talk about when the switch is on. But the next 3 slides, click. This won't be on a test. Now, when we look at this benzene or aromatic compounds, they have something called resonance energy. Now, when we look at benzene, these are harder to hydrogenate than cycloalkenes. This is a 6-membered ring with 1 double bond. These do not react as expected as 3 separate double bonds. There's something different going on. And this is true in all aromatic compounds. What's that difference? And it's called resonance energy, which is the name I like, the older name. They also call it stabilization energy. I don't like that name. Remember, slide is click off position. Now, this is the difference in the energy a real molecule has compared to the calculated energy of the most stable contributing structures. So if we were to take, again, switches off, benzene, and measure its energy, and then measure the energy by saying cyclohexane ring plus 3 double bonds, this is lower. Lower energy means more stable. And therefore, aromatic compounds are more stable than similar non-aromatic compounds. And the difference is due to resonance energy. Well, there's an important, what would be the right term? Ramification. I've used that word a long time. Look out, Dr. White's pulling out the 50-cent words. I don't know if you ever heard that. When I was a kid, if you used real big words, my parents or teacher would say, ooh, you're using the 50-cent words. But anyways, the ramification of that, oh, I've used it twice now, it's $1. But anyways, is that aromatic rings do not undergo addition reactions. The resonance structure stabilization energy is due from the fact that the 3 double bonds are sharing electrons together. Let's go way back. These electrons right here are holding hands to form the pi bonds of the double bonds. And you can say between these 2 carbons, double bond, single, double, and single. That's what calculus said. But in reality, they're really holding hands. We just show the double bonds to make it easier to think about. Hopefully nobody got any dizzy me running up and down the slides. All right, it's Bad Humor Monday. All right, now what they do is aromatic rings undergo what's called electrophilic aromatic substitution. Well, substitution, I change one thing for another. Aromatic, well, I'm dealing with an aromatic ring. What's this electrophilic? Well, electron, well, I know electrons have negative charge. Have you ever heard the term file? And file means lover. I'm an audiophile. I have 5 stereos in my home. because I love music. I love to listen to it. There's another type of file I don't want. They get arrested, but I'll let you figure that out. Oh, I see someone knows what I'm talking about. But anyways, electrophilic means it's something that's going to substitute one of the hydrogens on the benzene ring, and that something loves of negative charges. And where's there's a lot of negative charges? Right here, the pi electrons. Each one is 2 electrons. And here you see them in each of the p orbitals. And again, switch was off for that. So we have this electrophilic aromatic substitution. And again, switch is off for this slide due to resonance stabilization. You don't want to break those double bonds. You'll make it less stable compound. And when you break a double bond, like an addition, that's not going to happen. Aromatic compounds undergo substitution. And those are reactions, chemical reactions, where a hydrogen atom on the aromatic carbon is substituted with another atom or another group of atoms. And that they do. But even then, sometimes you have to catalyze it. So let's look at our first electrophilic aromatic substitution reaction, and that's halogenation. And I'll never ask the name of reactions, by the way, click, switches back on. If you take a benzene ring, react it with halogen gas, X2, and in reality, it's usually chlorine or bromine, because you need a catalyst, ferric trihalide, either chloride or bromide. What you do is replace one of the hydrogens with a halogen. You also make HX. Now, as you've seen already, organic chemists are biased. And biased in one way, I don't care about that inorganic stuff. Yeah. See, I'm biased. And therefore, on a test, I'd say give the organic product or product. So let's look at this reaction. By the way, I don't play on games on tests where I have, for this reaction, I put a iodine or fluorine. That this doesn't happen in the real world. I don't play games with students. That looks better. And I'm ignoring the inorganic HX. So if I were to do the following, and the catalyst helps make it more electrophilic, which I'm not going to go into on this reaction, how it does that. But what is this? Benzene ring. Ooh, halogen. Well, I do that like this, and ferric tri same halogen. Remember, X can be chlorine, bromine. Replace one of the hydrogens on the benzene ring with an X. Well, what's X? Bromine. And I make bromobenzene. Now, watch very closely. This is bromocyclohexane. That's not bromobenzene. You need I'd mark it wrong because you need the stuff, either the double bonds or the circle. One's benzene ring, one's cyclohexane. I had a student lose 10 points because she forgot to put the stuff that goes in here. Don't. You shouldn't. Remember, what you write has implications in organic chemistry. And these are two separate compounds. This is the benzene ring. This is a cyclohexane ring. We want to keep those double bonds there. So we've made bromobenzene. And here's one for you to try. Give the organic product or products. Notice I didn't say inorganic. Now, if you'd like to put the inorganic, feel free to do so. But I don't, because I'm an organic chemist. We're biased against inorganic stuff. Organic chemists are. Thank you, Ignacio. How's the weather in Florida?
I'm actually in Illinois right now.
Oh no,
So,
you changed states on me.
yeah, but I'll be
I
there.
asked, if you don't mind me being personal,
Yeah,
what city are you in now?
Elgin.
Oh, okay.
Yeah,
You know where that is.
yeah. So I'm
Not.
sharing the rain with you.
Okay. Well, now I know you're local.
Yeah.
Aren't you glad you were able to attend from out of state until you got back to Elgin?
Yeah, it was nice. The only thing is, I told you before, some colleges don't accept that online lab. So
What?
some colleges don't accept the online labs. So,
Were you the one who asked for my syllabus, or did you check? Well, with the pandemic,
yeah.
anyways, hopefully everybody will accept. I think I haven't heard any problems, but all right, let's do this. Andrew, are you done? All right. So I have a benzene ring. I'm reacting with a halogen. And notice right here, I also have a catalyst. And a catalyst, this makes a reaction go quicker. It's not consumed. And I replace one of the hydrogens in the ring, on the ring, with a halogen. In this case, it's chlorine. And here would be the answer. Now, I rarely do this, but if you want, you could use the circle too. If you forgot either one, the double bonds or the circle, I'd mark it wrong because that's cyclohexane. Now, there's something I'd like to explain to you. In organic chemistry and aromatic compounds, if there's something on the ring, sometimes we'll just call it a Z group. The switch is off right now. Oh, I just broke the switch. Click. This won't be on a test. And if I were to react this, say, with a halogen and ferric trihalide, there are a couple different products I could have. Up here, no, I don't have to worry because there's nothing on the ring. I could, and the switch is off right now. Where I have the arrow with the O, if it replaced the hydrogen on either one of those carbons, it would be ortho substitution. If I replaced it on these two carbons, it would be meta substitution. And if I replaced it with this hydrogen, it would be para. So it turns out there are two types of directors. One, depending on what Z is, gives you products that are ortho and para. The other, what Z is, gives you meta. Now, I could spend the next week and a half teaching you about different Z groups, and you'd probably get it wrong on the test. I know I tried that once long ago. And I thought about it and say, I'm not teaching organic chemists. They're never going to run this reaction or interact with it again after my class. So, by the way, Z is called a director. Switches off. Because based on the certain factors of Z, it tells the incoming group X where to go, ortho, meta, or para. And because of that, I'm not going to go into directors in our lecture. We'll have a lab in 2 weeks, I think it is, not this week, but next week, dealing where you learn about directors. But remember, whatever I do in the classroom, the lecture will never be on my test. Whatever I do or will be on my test. Oops, let me do that again. Whatever I do in the lecture will be on my test. Whatever I do in the labs will not. I keep them separate. And that makes the labs more fun. So what does that mean? Well, for this reaction, I've given you every example I could give you, because I'm only going to start with benzene. I'm never going to put something on there like toluene, ethyl, nitro, whatever. So I'm done with these. Let's move on to the next reaction. And that's called nitration. And nitration is where you take a benzene ring and react it with nitric, HNO3, and sulfuric acid, H2SO4, and you put a nitro group on the benzene ring. It's a substitution. Now, what I'm going to show you, you do not need to know for the test. And I'll cover it again when we do nitration reaction in the lab. Think of the sulfuric acid as H plus. This is a way of showing this acid. Let me write the nitric acid a little differently. Now, the lone pair electrons on oxygen will attract this. Again, this will not be on a test. To form this. And I put it in brackets because you can't really isolate it. When you put something in brackets, you can't isolate it. And if I look over here, what's 2 hydrogens and an oxygen? What's 2 hydrogens and oxygen? Hold on while I drink some water. Oh, wait. 2 hydrogens and oxygen, that's water. Whenever you form a stable leaving group in a molecule, it says, bye, I'm out of here. And you lose water. That's what minus H2O. And what are you left with? This nitronium cation. And that thing doesn't want a positive charge. So what does it do? It attacks the ring because there are electrons on the double bonds there. And it loses H plus. Here you added it. You'll get back H plus here. Your sulfuric acid, really. And guess what? I've done the only reaction I can ask you on test number 1, because I'm not going to do any directors. Now, important thing, in the nitric acid, it's HNO3, but notice how it loses water to become HNO or NO2. Remember, this should be a 2. Students put a 3 there because they see this which is wrong, and I mark it wrong. Nitro group, NO2. So that's the only reaction I can ask you on test number 1. So let's move on to the next reaction. This is called sulfonation. Sulfonation, you take a benzene ring, react it with sulfur trioxide and sulfuric acid. And similar to the way I showed you before, this forms SO3H+, which attacks the benzene ring. And notice there's no H2 here, it's SO3H. That's called the sulfonic acid group. And we'll learn later in the semester, by being able to put this on a benzene ring, organic chemists were able to develop the key molecule. Are you ready for this? In our laundry detergent. And this reaction helps make the molecules that are in your laundry detergent that make your clothes clean. Speaking about things at home, I forgot to do something. Time out for a public service announcement from your host, me, Dr. White. Actually, 2 announcements. Don't forget tonight from 5 to 6:50, I'll have my office hour. If you need any help, just come on by. 2, I forgot to ask. Oh, shame on Dr. White. Bad Dr. White. When you drove by a gas station, do you think about the fact that they sell alkanes in there? When you cook with your gas oven or stove, do you think about methane? Natural gas is an alkane. If you looked at baby oil or Vaseline, did you think about those are alkanes? Or did you light a candle and think half the weight of the candle is an alkane? Remember, organic chemistry is all around you. I stole that from SpongeBob. And it shouldn't hurt for you to think about organic chemistry outside of our lectures. So remember, next time you pass by a gas station, think about the gasoline they're selling is about half of the weight is alkanes. Or if you happen to use a barbecue, propane, the gas in the white tank they use to cook your meat or whatever else you put on your barbecue. Dr. White loves. Have you ever made barbecued corn on the cob? That is really good. We've been doing that in our family for many, many years. Or if you throw some vegetables on a grill too, you need a special grill pan for that. Like onions and things like that are really good. Asparagus grilled is really good. But the stuff in the white bottle, that's propane, that's an alkane. Back to our regular scheduled lecture. All right, so this is the only reaction I can teach you here. So I'm done. Benzene, sulfur trioxide, sulfuric acid, this is called benzene sulfonic acid, which I won't ask you to learn the name. And do I have time? I do. One company I worked for, we had what's called toll producers. And toll producers are companies who you don't have enough room because business is going good. You go to them and say, here's our product, will you make it for us? And then we sell it. And they're toll producers. I don't know how the word toll got on there, but anyways, that's what they're called. And this one company we had hired to make a derivative of this that we use as a catalyst for the products we made. And this is a pretty nasty reaction, having to deal with concentrated sulfuric acid. And I remember going to Birmingham, Alabama in the summer, as part of my job as laboratory manager, was to go to these companies that toll produce molecules for us and check they're doing a good job. And this company's plant was so dangerous, you had to wear one of those hazmat suits, goggles, gas mask, and 90-degree weather, 90-degree humidity. Those plants weren't air conditioned. It was not fun. Well, afterward, I gave them a clean bill of health and said, you guys are doing a good job, and I'll write a report. And they took me out to lunch. This is in Birmingham, Alabama, right before 2000. And most of you probably are too young to know about the Y2K. Y2K was when we hit the year 2000, computers would go nuts because supposedly Microsoft and other companies hadn't figured out when you go from 1999 to 2000 what the computer should do. Most people are wrong about that. Nothing happened. But if people were talking about the end of the world and everything, I mean, really, it was getting scary. And here I am driving in Birmingham, Alabama. They're taking me to lunch. I see this big billboard on next to the highway we're driving on, and it's for the Y2K gun show. And it said under Y2K gun show, get your guns before the end of the world and things go nuts. I still remember that decades later. All right, let's go on to the last reaction for aromatic compounds. Now, it hasn't for a number of years, but for many, many decades, if you invented or discovered a really important reaction, they named it after you. And two chemists, Friedel and Crafts, together discovered this reaction. And it's named after them. And let's take a look, and I'll write it on the other slide on my whiteboard, this reaction. You take a benzene ring, react it with an alkyl halide. Now, R is like X and Y in math. It means anything with carbons and hydrogens in it. It can be 1, it can be 5, it could be 500. Probably not, but it could be. And you need a catalyst, aluminum trihalide. And I think I do have it. I don't think anybody ever used bromide. And what happens is you do something very special, very rare in organic chemistry. You make a carbon-carbon single bond. I know about 500 general reactions, and of all those I only know a handful, about 20, where you can make a carbon-carbon single bond. That's something very special, very rare, very good too. And this is what you make. You also get inorganic stuff from here, but, and hold on one second. It would be more than 1 second. Give me a. Be with you in a second. I do have it as chlorine or bromine. And back to our regular scheduled lecture. Sorry about that. And what you make is a carbon-carbon single bond. Now, the bond between the benzene ring and the R group is to the carbon that has the halogen. The bond from the R group to the benzene ring is to the carbon that has the halogen on it. So let's take a look at this reaction. Remember, you still have the double bonds. So if you take benzene and react it with this and this, and let me remind you, I can write A plus B plus C makes D, or I can also write it this way. And that's what I usually do for these reactions, unless R is very big. And how do you do this? Well, you look for what's different. Whoa, here's a benzene ring. That's different. I've got up here carbon, 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 halogen. Well, carbons like this, I call R. So I have Rx, and notice I have aluminum trichloride. And X can be, in this case, it is chlorine. It could have been bromine. And you replace one of the hydrogens with the R group. And the carbon with the halogen will be the carbon bonded to the benzene ring. So what does this tell me? I have my benzene ring. Don't forget the stuff in the center. And how many carbons here? 3. Which carbon has the chlorine? The end one. Do you break carbon-carbon single bonds? No. So my R group is 3 carbons to the end one. I know there's 4 bonds to carbon. Remember, that's always your friend. And I'm done. And can everybody see this okay? Let me clean up something that we don't need. All right, let me go through this again. You have a benzene ring, and then we have this compound on top and the aluminum trichloride. By the way, this is called IUPAC 1-chloropropane, or common N-chloro and propyl chloride. I didn't teach you those names. When we get, it's not heavily used in organic. What you'll learn the rest of your life, or do. But anyways, the carbon with the halogen, and we have Rx. R is carbons, X is a halogen, chlorine, or bromine. And you put the R group on the benzene ring, substitute the hydrogen. In this case, R is 3 carbons, and the carbon with the halogen will be the carbon that the benzene ring is bonded to. And like I said, this reaction, not the specific one, but this general one, also helped lead to making your laundry detergents. And here's one for you to try. Give the organic product or products to the following reaction. Now we're getting some good stuff. Even though the stuff we've already done is good, we're getting to really interesting stuff. This in the coming chapters. Oh, am I happy? Thank you, Ignacio. Thank you, Andrew. Well, if I look what's different, ooh, I've got a benzene ring. That's different. Then over here, ooh, carbon-carbon halogen. I'm going to call this R. So that's Rx, where X is the halogen chlorine. And then right here, I have aluminum trihalide. And X can be, in this case, it is chlorine, or it could have been bromine. And you replace one of the carbons, one of the hydrogens on the benzene ring with the R group. And the carbon with the halogen will be the carbon bonded to the benzene ring. So what this tells me, I'm going to have a benzene ring. This is cyclohexane. Now it's a benzene ring. Don't forget the bonds in the center. What's my R group? 3 carbons. Which carbon is bonded to the halogen? The center one. So my benzene ring will be bonded to the center there. And this is very important, which carbon you place it. If you notice the example before, the halogen was on the N carbon of 3, and you got N-propylbenzene. Now, when it's the center, you get isopropyl. And something like that can make a big difference. I'll teach you later how 1 carbon difference almost killed a lot of children. But not this chapter. All right, let's try something else. On test number 1, I'll have one synthesis problem, and all the reactions are fair game except for combustion. And the question would be, what 2 things do I react to make this compound? And I'm also using this catalyst. So how do you do that? Well, what's different here in the molecule I'm trying to make? I've got a benzene ring, that's different, and it's substituted. It's got carbons on it. I'll call that R. And right here, I have aluminum trihalide, and X can be chlorine or bromine. And what do I start with? Even though I put it on top of the arrow, I can say a benzene ring plus an alkyl halide. So one of the answers here is a benzene ring. And what do we have here? Here's our R group. Which carbon is bonded to the benzene ring? That one. Here's my R group. And which carbon has the benzene ring? The center of those 4. And what's my halogen? Bromine. And that's how you do it. And therefore, if you take this molecule, react with this catalyst, you will make that compound, T-butylbenzene. Oh, I better let you have some fun. That's better. And what two things would I react to make this compound? Your turn. And this is the fun part of organic chemistry synthesis. But I'm biased. I'm a synthetic organic chemist. All right, gentlemen, thank you. And if we look here, what's different? Ooh, a benzene ring, and it's got carbons on it, an alkyl group. And I'll call this R. Oh, I have aluminum trichloride. And we show halogens for this reaction can be chlorine, which it is, or bromine. And what do I start with? A benzene ring plus, what's my second thing? Rx. Therefore, one of these question marks will be a benzene ring. And the second one, what's my R group? 2 carbons. And the end carbon, the carbon bonded to the ring, benzene ring, will have a halogen. What's X? Chlorine. And that's how you do it. Any questions? All right, listen carefully. As of now, I have finished all the material on test number 1. I always try and finish about a week earlier, which I have, because don't forget, I could have had test number 1 on Wednesday. That's not fair to you finishing up now and then making you rush to learn, which is why I postponed it a week. But all the reactions and material I've covered. Now, there's one other thing I'd like to talk about in aromatic compounds, switches off, but this is interesting. That's polycyclic aromatic hydrocarbons. Those are aromatic hydrocarbons with more than one ring. Now, I stayed away from it. You can have molecules with rings that share carbons. And this has 2 rings, but they share carbons. And we call those polycyclic, or sometimes I'll say 2 rings fused together in this case. Now, one polycyclic aromatic compound is this one. Don't forget, it switches off, and that's naphthalene. And naphthalene has 2n plus 2 pi electrons, so it's aromatic. And that reacts somewhat like benzene, but the main use for that molecule is for mothballs. Mothballs are naphthalene, which is a white solid at room temperature, pressed together to make these little balls. And for some reasons, moths will attack wool and destroy it. don't like this. Now, I don't like wool myself personally, so I don't have any naphthalene mothballs in my house. But when I was a kid, my parents and grandparents had drawers where they kept their woolen goods like sweaters, and they had a bunch of mothballs in there to keep the moths and other insects from eating them. Now, a special aromatic compound, polyaromatic compound, is graphite. Remember, switch is off. That's not what I want. And graphite is this material that is used for a lubricant. And graphite is made up of sheets of six-membered rings fused together. Now, what they don't show in here are the double bonds, and these are polyaromatic compounds. Now, the interesting thing about graphite, remember, switches off, and I can go about a minute or so. I got 2 minutes. I got time. It's like pieces of paper layered on top of each other. Now, how many of you have ever written with a lead pencil? Either mechanical or wooden. Guess what? There's no lead in them. Back about 100 years before or longer before, back in the Roman times, like 200 minus 200 BC or BCE, whichever you'd like to call it, they had lead in, they used to write. Guess what? Lead's poisonous. I don't know exactly when, but they found if they took graphite, mixed it with clay, and made it into rods and put it in wood, or now put it in mechanical pencils. Can you see that? The tip? That will leave sheets of from the graphite. Each one of those sheets is called graphene. And that's what you're doing when you write on paper with a pencil. You're leaving sheets of a polyaromatic compound on there. Now, how am I doing time-wise? Oh, I got a minute left. Now, it turns out that, and do I have any paper? I do. They found out, and about only 15 years ago or less, maybe even 10, two very intelligent scientists, people said you couldn't take out the one sheet from the graphite to the graphene. And they found if they put Scotch tape on those big hunk of graphite and pulled it off, and then threw that in a solvent to dissolve the glue in the Scotch tape, you could make sheets of graphene. And they won a Nobel Prize for that, rightly so. Now, also back in about 95, a researcher in Texas, another one in Japan, independently found you could take graphite, that black rock, and react it with certain strong chemicals to make the sheets of graphene into tubes. And these are very tiny, nano centimeters. They're called nanotubes. They're tiny, but they're as strong as steel. And there's a lot of research been doing for many years now, and a lot of money thrown in from our government and everybody else's into nanotube technology. With that, I went a whole minute over. Sorry, I'm done for today. Don't forget, on Wednesday, I'll go through the aromatic problem set, so please do it. And with that, I'm going to say, unless you come to my office hour later today, gang gesund. Goodbye. Bye now.